Okay, guys, this is Mr. Hayden. This is chemistry, week 13. Just so you guys know a few things, it's week 13, and basically week like 19 or 20 is our last week. So we have only like 7 weeks left, minus 1 day for May 25th, and then the last week, I think you do your final either I think on Monday or Tuesday or something like that. So you really don't have a full week. So really, you guys don't have much time left. So if your grade is an unhappy face, and you want it to be a smiley face, you're going to have to do something about it and make sure you bring those grades up. If you contact me and say, hey, can you help me with a lab that I didn't decide to show up to, hadn't done until now, or I haven't contacted you till the last minute, can you please help me? I'm just going to answer that one with no right now, just in case you need to know. Because some people seriously haven't done labs that are due back in the day, and I do them here, and then they say, well, I don't understand it. And I go, me either. We should really move past that. So I'm going to go ahead and make sure I make that statement now that if you haven't done a lab in the past, and you decided not to wait, you waited until the last minute because you either did not care or you just wanted to blow it off, good luck on it on your own. You can do it on your own. It's pretty laid out for you inside the lab guide. It's really step by step, but we won't do it. All right, so remember, get your grade up, and science notebooks, just so you know, will be due probably the second week of May. I have to verify that, but I think second week of May, I'm going to give it a 2-week lead time to be able to get you guys to get it and drop it off, and or mail it if you have to, but I prefer you to bring it in so I can give you feedback, of positive or negative feedback, depending on the situation. All right? So, all right, so the essential question today, actually this is a very hard essential question, but we're going to still go, is what are the main factors that affect reactions, and explain how each of them cause an effect on the reaction, okay? So what causes reactions, also what affects them, and explain. Really not that huge or crazy of an idea. And today you'll kind of see that it's really simple. Actually, the concept is just something you just have to make sure you write down and understand. Okay. Good talk. Shall I leave that up in case you guys need more questions? You got a pencil? You good? So again, what are the main factors that affect the reactions, and explain how each of them affects, and basically explain them. All right. I don't want to simplify it by saying explain them, so I don't want to draw it out to make it long-winded. It's important to be long-winded when you're a teacher. They teach us that. They say, how can you make the question super hard and make it so they don't understand it? And then also, how can you make them do busy work and fill the rest of the hour just so it looks like you're doing your job? Agreed?
Not really.
No.
Meeting your homework.
Your face, Ryan Gosling. Sorry, there's a little bit of trivia crap going on as well as learning. Apparently that's an app that I learned about, and so and I'm killing it. So far, I've almost all been right. All right, so again, make sure you write that central question, and we'll get going. If you have any questions, please make sure you ask them. But basically, we're going to talk about, again, what actually affects the chemical reaction. So, obviously you put some stuff in the stuff, and you put the solution in here, and stuff happens, it creates a bubble. And we've been doing chemical reactions, looking at stuff like last semester and this semester, but for some reason, now they're telling you how it actually occurs. Very, very backwards, but it's the way out. We talked a little bit about all of them, but they actually put it into a unit to make sure that you are kind of responsible for it. So the reactant particles must collide with each other. That sounds really, really complicated. It means the stuff you put together needs to touch. They need to go bang, bang against each other on molecular level. They have to hit each other. Next, the collisions must be enough energy to overcome the energy barrier called the activation energy. And remember what the next slide is. What it is that you can put two chemicals together, but sometimes it either needs to have a certain pressure, needs to have a certain temperature to it, or that's all happens. That's why some of them need to have energy to hit a certain platform. As soon as they hit that point, reaction occurs. If it doesn't hit that point, there's just two chemicals chilling with each other, hanging out like friends. And also, the reactants must form new bonds to produce products. Example, if I put two solutions together and nothing happens, cool. If I put water, which is technically a molecule, right, H2O, and I put oil, make vegetable oil, which is technically another molecule. Okay? You did well. Did you win? Did you lose? You lost it, didn't you? And then you have those, they don't actually ever do anything. Even if you boil it and you change pressure, they don't collide, they don't create reactions, they don't create a product, and that's what that last one says. Okay, so the activation energy, just real quick, it's the minimum energy required for a chemical reaction. So example, if I take wood, okay, I got wood on my desk, okay, I got wood on my desk. Then let's say, okay, I'm going to go ahead and take wood, I'm going to go take some oxygen, I'm going to throw a little oxygen on there, cool, and then I'm going to take a match, and I'm going to set it right next to it, and I go, fire! It's nothing happening.
Think about being able to take a left.
Fire! All right, but think about it. If I took the things that create fire, or the things that I'm trying to create, basically carbon, leftover dust, and CO2 and all those other stuff. And that's what I'm trying to create. That's what happens when you burn wood. But I put all this stuff together and nothing happens. I need to actually what's called overcome the minimum energy requirement. You need a certain type of energy, a spark, a certain amount of energy to actually create the fire, which is going to then burn and create the wood to be burn the wood into, like, say, charcoal or whatever else you're trying to make out of it. So there's a certain threshold. Once that threshold is actually met, then the reaction occurs. Anytime before that, it's just chilling there, okay? Just like even it says gasoline for your car would ignite as soon as it came into contact with air, burst into flames, and everything would be bad. Think about that. Gasoline. You can have gasoline just sitting there. It doesn't do anything. It just chills. You can even warm it up. It just chills. But as soon as I create a spark or something that can ignite it, it moves the energy level to the point where it combusts. That's what your car does. Those little spark plugs that you probably, you guys don't know, maybe you do know or don't know. There's spark plugs you think that are screwed into the top of your manifold that literally just sit there and spark. That's their only job. Just all it. Just fun stuff, right? But it creates that activation level. Here's a little bit of that. If you have the reactants, and the way to read this graph is on the far left, you see the reactants. They'll just kind of chill there until you raise the energy levels to a certain point. It will react it, the reaction will occur, and then after the reactant's all been used up, the product will then usually become completely different product as well as energy level. It will either give off energy or take in energy if it's endo or exothermic. So that's pretty good there. Okay, so changing the rate of chemical reaction. To change the rate of chemical reaction, one or more of the following have to occur. So I want to change the rate. I want to have them faster or slower, depending on what I'm trying to do. So example, you guys have those little glow sticks? You know those little glow sticks in your team? You're like running around. It's really, okay, remember yesterday when you guys were doing that? Okay. Well, those reactions are, if you were to break those, like you humiliate those little, you have to break it in half. It's not really break it, because then it's weird if you get the stuff all over your hand. It makes some of that. But if you break it, you're actually breaking a little tube inside of it to make the chemicals touch, which then creates a photosynthetic reaction. Did you know that you can actually speed up the reaction? You can make that thing wear out faster if you wanted to. Boil it. It'll make the reaction occur faster because you're speeding up the molecule. The collisions take place faster, and it'll go down faster. It'll be bad, no good, throw away. Or, like I do, I let them play with it for like, an hour or so, and I put it in the freezer. I slowed down the reaction at this point. Then I take it out of the freezer, I let it thaw, and guess what? It's lit up again. And it lasts 4 weeks that way. Okay? It has a certain amount of time that it's going to react. You can either speed up or slow that down based on temperature, which will be done in a second. So increase the energy, increase the number of collisions is number one, which means you can do that by either speeding up by heat. You can either put more reactants in there to create that. You can limit the space of the reaction. You can increase pressure. There's all this stuff we're going to kind of go with. It's how do you get them close to each other? How that is. Increase the energy. That is just pretty much straight up. Okay, increase the energy level. And then the third one is decrease that activation level. Means the fact the reaction will have, there's a certain time it actually occurs. If you add something to what's called catalyst, it actually takes that energy level and reduces it. So not as much energy is actually needed to make the change. Not as much. If the change still occurs at a level, it just reduces that. So you can actually get that a lot faster. Your body uses a lot of catalysts within itself. just so you're not using so much energy staying alive. Because you're just sitting here right now and staring at me, which is awesome because you look at me. I mean, look at the beard. It's amazing, I know. But in general, it takes a lot of energy to do that. Your brain uses 25% of your being. A lot of energy. So your body has to use catalysts. If it doesn't use catalysts, you would be tired all the time, eating all the time, and you couldn't actually do it. So it's important that your body is able to reduce that limit. Okay. So a couple. So to define the rate of chemical reaction, you must be able to follow its process at the time. You have two choices. You have to either increase the product. Actually, let's see here. Sorry. Actually, you guys don't even need to know that. Apologize, sir. All right. When you look at this right here, if you have a contained environment, so you have a enclosed reaction, you have a pump, which is basically what this pen is right here, a pump as well as a other closed reactivity. What you can do is you can actually push molecules together by increasing the pressure. The more pressure, the closer the molecules together. We're actually going to see this. I'm going to show you guys a simulator. And we'll be able to play with temperature, we'll be able to play with concentrations, we'll play with a bunch of stuff. And you actually can see it taking place. But if you have a certain pressure, the reaction will occur however it is, whatever that rate is. As soon as you increase that pressure, and now there's not enough room, they start bouncing around quicker, increasing pressure, because we learned that through all the laws. Reactions faster. Okay. More pressure, faster. Less pressure, less faster. Believe it or not, you can boil water. I believe that if you change the pressure of the actual environment around the water, temperature of the water boils a different. It changes temperature. It's not 100 degrees. It changes based on the amount of pressure you have. Oopsie. Okay, so here's just a reaction of how it takes over time. It'll be fast at first, and the reaction will actually slow down or stabilize after all of the reactants have kind of ran into the other reactants and created a new product. If for whatever reason there's an additional product or additional reactants left over, say you're doing sodium chloride, you have all the salt now in this little stuff. You have a whole bunch of sodium left over. Like, oh, God, I got all the sodium left over. I'm going to buy it. How can I? What do I do to get rid of it? Think about that for a second. I got sodium chloride together to make salt, right? I have a bunch of sodium left over. How do I get rid of it?
I don't think you want to throw it in the trash. So
Kind of a trick question. I add more chloride to the sodium to make more salt. Sometimes when you add them together, stuff is left over. And if you want a full reaction to occur, you need to figure out how many moles you actually need for a full amount to be reactive. That's why you do the whole mole ratio of exactly how much reacts to what. That's what a balanced equation is. A balanced equation is this plus this equals this. If, say, I said it's sodium chloride, it would equal salt. But then it says plus chloride, like the extra chloride is hanging around, I need to add more sodium to go over that. Vice versa. That's why you balance equations to make sure you get that exact amount of moles you need for each one of those to take place. So another one too that people don't think of is surface area. How big is the molecule? Is it a big molecule that needs to be broken into a smaller molecule before it'll react to what you want to become? So example, this is a bigger molecule, but if you look inside of this molecule, there's actually stuff in there, the salt. But nothing's going to hit it. I mean, if I run into the outside, I'm never going to hit the inside. So we need to be able to break that down into smaller portions, which increases your surface area. So all I have to do is break it down into, say, the 4 sets. Now, my surface area here is much larger. If you were to calculate that, it's like 4 times the size now, because I can now reach the inner part. Now I can reach the bottom here, this inside here, all this. I can actually hit those now with other reactions. Sometimes when you have something, so you want to have one type of reactant and make a product on the road. You have to take the product, put something in there to break it down into smaller portions. Then you take a smaller portion, put this reactant to create finally. It's like all these steps sometimes you have to take. That's why when we did last week, we did that weird math where it was like figuring out, breaking it down, the big equations into the smaller equations and make them all equal to each other. We did last week. That's what those are. This reaction makes this. This reaction makes this. This reaction makes this. In this order, and that's how you get the product. It's not just put them all together and it all starts clapping. Which I know you guys got excited when reactions occur. Okay. So again, same concept. If you have this type of hydraulic pump and you have pressure, the increased pressure will decrease the amount of volume. Therefore, the amount of reactions will feel to bang each other more. So there's the concentration. I think the better thing to do here, guys, let's just jump to the activity, because it's going to show you exactly how we can play with it and get it done. So let me go ahead and share this with the rest of the kiddos. Is that it? Where is it? Did you guys see that on the list? All right, let's see. Let's try this. All right, so we're sharing here. I'm going to run it. By the way, have you guys ever been to this website, PHET? It's a nerdy website. We can do a whole bunch of simulators of. Okay, do me a favor. If you can see a simulator, please give me a smiley face. Perfect. So no smiley face. So you guys cannot see a simulator right now, because that's the problem, is that I don't know what you guys are seeing right this second. Okay, cool. So you don't see it. Awesome. Good talk. Let me go through and see if I can figure out the sharing component. Tools, sharing. I want to go and stop sharing. Okay, go back to here. Let's go ahead and start sharing again. What is going on? Why can't I see it? You know what? I'm going to share my desktop. Okay, so can you, in a second you'll be able to see it, I promise that, because I just shared my desktop. Okay. Give me a second. Okay, do you see a simulator just popped up? Smiley face. Hey! Approving, good. All right, I'll just go ahead and now jump away from here. Let's see what you said. Okay, cool. All right, so here's the simulator. Now, what this simulator does is allows me to basically get different situations. So what I can do is I take this little ping pong ball, I can pull the knob back. Pew, pew, pew. It is just reactions taking place. That's all this is. Now, if I went ahead and put, okay, I want to put a smaller one. Pew, 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 pew. I'm having fun. I'm sorry, guys. But I can go ahead and, it's going to a certain thing, but if I go ahead and lower the temperature by bringing ice in, okay, the little thing on the top right-hand corner of that, it's showing the temperature dropping. What's happening is, as I am lowering the temperature, the kinetic energy obviously goes lower. Now, a question for you. If the kinetic energy goes lower, do you think the reactions are more or less? Are they hitting each other more or less? What? Less. Now, if I just add fire, because I just added fire now, that's me adding fire. All right, and then as it increases, what you're going to see is the kinetic energy increase. You're going to see more. Now, if I went ahead and said, okay, many collisions, I'm going to go ahead and just, I'm going to put some, should I put some BCs or ABs? ABs is the first one I heard. So I'm just going to pump a few of these in there. Okay, so there you go. So I'm lowering, now I'm going to lower the reaction rate by adding ice or lowering the temperature. You can see that they're going slower. They're not nearly as fun. They're kind of boring now, right? Now if I go ahead and raise the temperature and go fire, fire. So I'm adding, now what I'm doing is I'm adding temperature. Now you can see that as the temperature rises, it's like giving a kid candy. Okay? They're going to be bouncing off the wall. Look at it. Woo! 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 All right, and then what happens if I add more? Boom, there's just more. Okay, I'm adding more reactants. You're seeing more. So I'm going to add a whole bunch of reactants. Ready?
Okay, do you think there's a lot or little reactions that could take place? I'm going to add another one. Right away, you see that they become an automatic molecule. Now I'm going to add some. You can't even see them because they're already attached. Now if I go say, okay, I already added all of my stuff, everything's crazy, let me lower the temperature now. So I want to lower the temperature. You see the energy level, how it went down and up, this area right here. If you increase the temperature here, right, at that point or lower, no reactions occur. They just all bounce around each other. But as soon as I add enough energy, goes right above that little threshold, it starts to occur. So here we go. Let me go ahead. What do I want to do? I want to lower temperature. I want to see what it looks like. I want to see what these things look like now. So obviously, they all kind of came in and reacted to each other, but now they're slowing down. Temperature effects. You guys see that? I mean, pretty straightforward, I think. What else was there? There we go. So I'm going to add some C's. Let's do this equation. So I'm going to add A, 1, 2, 3. Okay. So I added how many? 6 total. I'm going to do some BC's. 1, 2, 3. So there's an equal amount, correct? Nothing's going to occur. They're just going to bounce off each other. Why? Why are they not reacting with each other? Why aren't they grabbing on each other and going, do the thing out? They are very shy molecules. Yeah. But why? Thank you very much. Appreciate the additional input from my homeroom students. I would like to point that out. All my homeroom students are smarter than all other homeroom students. I'm just kidding.
And slowing down the energy after a reaction reverse some reactions, or will it never move the same reaction?
Relax, guys, chill. So they're starting to combine now? There you go. So you said if after they combine, I lower the temperature, what happens at that point? The reaction occurred. So when it slows down, it's now slowing down that molecule that's together. It won't reverse. To reverse, you either need an additional catalyst to go backwards. If it's reversible, a lot of things like molecules aren't reversible. They take some energy and some recourse to go back. Like you have to react with this product, then react with this product to get back to this product. So no, you can't just lower it and it reverses. What's going to happen is you're just going to increase because you're not increasing really it happening, you're just increasing the banging into each other to create this molecule. Once it's made, it is. Just like when you make a car, to reverse it, it's kind of hard. Like take a ring apart and come back together. Similar when you do the same. So you can see right here, it's going to work, and they're all starting to attach to each other. And if I add more of the one product, so if I add more of A, now what you'll see, if I start increasing a whole bunch of A's, does it speed up or slow down? The bouncing. It should be speeding up because what's happening is I'm increasing the reactant's concentration. Now there's just more stuff. If I took people and I said there's like say 50 people in this room dancing, 80s music, because that's what we do, right? That's what we do. I don't know if you do that or rave music, whatever. And then I started putting more people into the room. You guys would be bouncing into each other a lot more. Energy level would go up. The kinetic energy would go up. The temperature in the room would all go up because of all this stuff. Molecules are the same way. If reactions are occurring in exothermic, there'll be an increase in temperature. The more of the product, more of the reactants, the higher the product output. So let me go ahead and get this real quick. Let me go here. Just so you know, if you guys get super duper duper into it, I'll go ahead and copy and paste into the website so you can go there and use it. There's various ones. This is color, and this is like gravities and other things. But Go ahead and stop the sharing now. All right, by the way, this is a picture of what the catalyst looks like. It's kind of what I said before, is that the catalyst makes things happen faster. It takes the rate, which is a higher rate for the red line, and reduces the amount of energy needed for the reactant to occur. If it does, good. Sometimes you add it together and it's not a catalyst, you just put extra stuff in there for absolutely no reason. You actually have to specifically know that this is a catalyst for this. And that's you need to figure it out over time. Okay, let's go ahead. Okay, so if you have any questions, make sure you ask them. I'm going to go around and check the essential question for the people in the class. The people at home, go ahead and drop that into the Dropbox for week 13, please. And go ahead and have a good rest of your day.